Okay, let's start. Okay, শুরু করছি। And basically, in my portion and in structural mechanics too, we'll discuss how to find the deformation of the beam or deflection of the deflection of the beam. Okay, in your structural mechanics one, you know how to find the shear force and the bending moment. And this shear, but question is why this shear force and bending moment is required. Okay, the answer is basically this shear force, bending moment, and deformation is required to design the beam. That means you have to provide the cross section of a beam in such a way that in such a way that it can resist the bending moment and the shear force as well as deformation. Okay, and in this first figure the continuous line shows the initial position of the beam, and the dotted line shows the position of the beam after deformation. Okay, generally what we represent the beam by a single line, that is the centroidal axis of the beam. Okay, in figure 2, this continuous line, it is the centroidal axis of the beam before deformation, and this dotted line, this is the centroidal axis of the beam after deformation or after the application of the load. And the centroidal axis after deformation is called the elastic curve. That the elastic curve means the centroidal axis after the deformation of the beam. But question is why this deformation is required. Okay, and we know that the cross section will be such that a deformation will such that a deformation it can resist the deformation, and apart along with the shear force and the bending moment. Again, if the structure has excessive deformation, the secondary stress will develop within the structure. Okay, that's why we
Sir,
try to
what is secondary stress? Can you explain?
what.
Sir, the secondary stress.
Yes, just a minute. Let me explain. Okay, in the yeah, what is the primary stress? That is the primary stress mean the stress due to the application of the due to the direct applied load. Okay. Similarly, this is the one part of the stress. Second part is if the structure deflect too much, or if the deflection of the structure is excess cross some limit, then there will be the stress apart from the stress due to the direct force. This stress due to the excessive deformation is called the secondary stress. This is not for the direct loading. This is the indirect stress. Okay, for direct loading, the stress will develop. It is called primary stress, and if apart from this direct loading, if the structure deflect, the deflection will be, if this the deflection ex, cross the certain limit, then the due to this excessive deformation, the stress will additional stress will develop within the structure. This additional stress is called the secondary stress. And how the secondary stress is how much secondary stress is developed, that depends on the deformation. Okay, and that's why during this design we try to restrict the deformation within a certain limit. That's why the need for the that's why the calculation of the deformation is required during the design procedure. Okay, in the beam, these are the two deformation. That is, one is vertical deflection and second one is slope. What is vertical deformation? This is the distance between the centroidal axis as well as the at the and the elastic curve. That means the distance is the vertical deformation is the distance between the point on the undeflected axis and the corresponding point on the elastic curve. This is the deformation, vertical deformation. That is, we can call deflection delta is the vertical deflection. Okay. Similarly, the slope is the angular deformation. Okay, angular deformation. This is the slope is the angle between the tangent of the elastic curve at that point and the undeflected beam axis. That means if we try to find out the slope at point C, then we have to draw a tangent on at that point on the elastic curve. This is the this C and C D dash is a tangent on the elastic curve at point C, and this D line, the CD line is a parallel to centroidal axis before deformation, and angle between these two will be the slope of this slope at this point C.
So
Okay, that
these
means
points are variable, right?
what?
Vertical deflection and slope will change with position.
Yes. It depends on the position of the point. Okay. If say will say change, this is the elastic curve. Okay. If the point C will change, then again the deflection as well as the slope again it will change. Okay. That it depends on the position of the load. Oh, sorry, position of the point. Okay. Okay, these two are the main deformation. That one is deflection, vertical deflection, another is slope or angular deformation. Okay, these two we have to discuss. We discuss how to calculate the vertical deformation as well as the slope on the slope of the elastic curve. Okay, but this in this method, but here the deformation this the vertical deformation as well as slope, we measure the vertical deformation as well as the slope with respect to the initial centroidal axis of the beam. Like that means we consider this initial centroidal axis or centroidal axis before deformation as a reference line. With respect to this line, we try to find out the vertical deflection as well as the slope. Now, what we try to find out in this here we try to find out the equation of the elastic curve. Once we get the equation of the elastic curve, from this elastic equation of the elastic curve we can easily find out the deformation as well as the slope at a particular point on a elastic curve. Okay, that here that's why we try to find out the equation of the elastic curve. Here we consider the x-axis, the positive x-axis and positive axis in this way, that is the x is positive towards the light, towards right. Similarly, vertically upward, y is positive. We consider the portion of elastic curve, that is p dash. It is a portion of elastic curve, and the distance between the p and p dash, along x-axis it is dx, and along y-axis it is dy, and along the curvature the distance is ds. And this curvature, this position this curvature or this portion of the elastic curve make an angle d alpha at the center, and the radius of curvature is r. Radius of the curvature is r. Okay, now what we can write from this equation, we can write ds square is equal to dx square plus dy square, or ds is equal to root under dx square plus dy y square. Similarly, if this angle is d alpha, we can write ds is equal to r d alpha, or r d alpha is equal to, if we compare these two equation, from there we can write r d alpha is equal to root under dx square plus dy square, or similarly 1 by r is equal to d alpha divided by root under dx square plus dy square. Similarly, if this angle is very small, this alpha is very small, we can write or we can write tan alpha is equal to dy dx. Tan alpha is equal to dy dx, and if we differentiate this equation, tan alpha is equal to dy dx, that becomes d2y dx2 dx plus 6 square alpha d alpha. 6 square alpha d alpha, or d2y dx2 dx is equal to 1 plus tan square alpha multiplied by into d alpha, or d alpha is equal to 1 divided by 1 plus tan square alpha d2y dx2 dx, or d alpha is equal to d2y dx2 dx divided by 1 plus dy dx whole square. Similarly, from equation 1, that is r d alpha, what we already have r d alpha is equal to root under dx square plus dy square. Just put the value of d alpha in this expression, that is r into d2y dx2 dx divided by 1 plus dy dx whole square is equal to dx root under 1 plus dx dy dx square, or what we have, that is r d2y dx2 divided by 1 plus dy dx whole square is equal to root under 1 plus dy dx whole square, or 1 plus r is equal to d2y dx2 divided by 1 plus d2 dy dx whole square whole to the power 3 by 2. This 1 by r is the radius of this r is radius of curvature, and we can simply consider as 1 by r is a curvature. 1 by r is nothing but it is a curvature 1 by r. Now here we have a expression for the curvature, that is 1 by r is equal to d2y dx2 divided by 1 plus dy dx square whole to the power 3 by 2. Now in this expression we do some approximation by assuming something. Okay, what are the assumption? In this expression, what we can assume, that 1 plus dy dx square 1 plus dy dx square is almost equal to 1, and it can be on it. This can only happen if we assume that a value of y, that is value of y is nothing but it is a deformation of the beam. If we assume that a deformation is very small, and our problem is small deformation problem, then 1 plus dy dx square is equal to 1. That means here we quantify the deformation as a small, that when we consider 1 plus dy dx square is equal to 1. Just a minute. Okay, that means in case if you assume our deform, we can and we can differentiate our problem as small deformation problem as and the large deformation problem. If we assume the deformation is large, then 1 plus dy dx square not equal to 1, and if it is small deformation problem, then 1 plus dy dx square is equal to 1. In most of the cases we consider our problem is a small deformation problem, it is not a large deformation problem. Then the equation 3, or equation for the curvature, that 1 by r becomes d2y dx2, that is d1 by r is equal to d2y dx2. It is true when the problem when we assume that a problem and the problem is small deformation problem. If it is not, or if we assume the problem is large deformation problem, then 1 by r should be d2y dx2 divided by 1 plus dy dx square to the power 3 by 2. Okay, now we assume we simplify the equation of the curvature by assuming the problem as small deformation problem. In most of the cases our problem becomes a small deformation problem. Okay, that means that's why it is 1 by r is equal to d2y dx2. Now we take the help of Bernoullis equation, that is 1 m by I is equal to E by R is equal to sigma by Y. What is the Bernoullis equation? That is m by I is equal to E by R is equal to sigma by Y. M is moment of inertia, sorry, moment. I is moment of inertia, is modulus of elasticity, R is radius of curvature, is equal to stress is bending stress, divided by Y is the distance of the point where we want to find the stress from the neutral axis. That is the Y is nothing but distance of a point from the neutral axis. Okay, this is the expression for the expression of Bernoullis equation, or we can say this is the expression. This is m by I is equal to E by R is equal to sigma by Y is the expression for pure bending. For the pure bending, just remember that I think you know this expression, and it was in your structural mechanics one, that is m by I is equal to E by R is equal to sigma by Y. From this expression, what we can write on m by I is equal to E by R, or m by I is equal to E by R, or m by I is equal to, just put the value of 1 by R, that is E is equal to d2y dx2, or m is equal to ei d2i dx2, ei d2i dx2. dx2, what is d2i dx2 is the curvature. That is the relationship m is equal to ei d2i dx2. It is a relationship of the between the moment and curvature. This is a relationship between the, again I repeat, moment and curvature for small deformation problem. Just remember, if I write, if we write m is equal to ei d2i dx2, m is equal to ei d2i dx2, this is for small deformation problem. We quantify the small deformation problem in this way, that is 1 plus doi dx square should be equal to 1. Okay, now this we will use this expression to find out the value of y. Now, next the sign convention. What sign convention? We in sign convention, what we during the calculation of the bending moment, we assume that this is the positive bending moment. If we assume the bending moment as positive when it is sagging in nature, and the direction of the sagging moment will be like that. If we calculate the bending moment from the left, then the clockwise moment is sagging moment or positive moment, and if we calculate the bending moment from the right, the anti-clockwise moment is considered as sagging, and or it is positive bending moment. Okay, in this expression, that is m is equal to ei d2y dx2, what we have, we assume that positive x is positive, towards the left is x is positive, and y should be considered as positive when it is vertically upward in direction, upward in direction. Similarly, slope will be positive when it is anti-clockwise in nature. Anti-clockwise in nature. Just remember, this sign is not correct. We have to do a correction. The slope is m is equal to ei d2i dx2. It is valid when the slope in this expression, the slope is considered as positive when it is anti-clockwise nature, because if your x is towards the left is positive, or y is vertically upward is positive, then the anti-clockwise rotation should be considered as positive. This is not correct here, correctly written here. The slope will be is positive when it is anti-clockwise in nature. Now, in most of the cases, if Moses, the beam is subjected to the vertically downward load, that means the deflection always occurs in the vertically downward in direction. Downward in direction. Then that means we have to consider the axis system in this way. This is x remain positive if it is towards the right is positive, but y is the vertically downward direction is considered to be positive. If it is so, if x is the positive x-axis is like this, and the positive y-axis is vertically downward direction, then the slope will be the clockwise in direction should be considered as positive. The slope will be considered as positive when it is clockwise in direction. Okay. Now this is the sign convention for this axis system. Okay. Now we try to write this expression. This is m is equal to ei d2y dx2 in this axis system. Okay. Now what we will do, we will just if the elastic curve will be like this, or bending moment is sagging in nature, if the bending moment is sagging in nature, the elastic curve will be like this. This is the elastic curve for the sagging bending moment. Now, if the sagging elastic curve is like this, then at point left hand side point, the slope is positive. Okay, because it is clockwise in nature. Similarly, the slope at right hand side point, the slope is negative because it anti-clockwise in nature. That means if we move from this left point to the right point, right along the x-axis, along the positive x-axis, then the change of the slope, that is what is change of the slope along x direction, it is positive in nature, because at left hand side point, that is left hand side point, the slope is positive, at the right hand side point slope is negative. That means if we move from left to right, or if we move along the positive x-axis, then the change of slope or dy dx should be negative in sign. What is this dy dx? This is d2y dx2, d2y dx2. We
Hello,
can,
sir. I have a doubt.
Just a minute.
Okay, sir. Okay,
Just
sir.
wait.
Okay, okay,
And
okay, okay.
dx of dy dx, or what you can write, dy dx is nothing but this is the slope, that is theta, or you can write d theta dx is equal to d2y dx2. What is d theta dx? This is the change of the slope along the direction of x-axis. This is d theta dx is the change of the slope along the direction along x-axis. Now come to the figure number A. This is figure number A. At the left hand side point, the slope is positive, and right hand side point, the slope is negative. That means the change of slope along along the positive x-axis, it is negative, because at left hand side point it is positive, and right hand side point it is negative. That means if we move from left to right, the change of slope is negative. That means dy dx is negative, or d2y dx2 is negative. But the moment it is a condition of hogging moment, that is it is a condition of sagging moment. If your moment is sagging, then the curvature will be like this, the elastic curve will be like this. That means the moment is positive, we have d2y dx2, it is negative, but moment is positive. Then to balance this sign, we have to introduce a negative sign at the right hand side of this equation. That is, then m should be equal to minus ei d2y dx2. এবার বলো কি কার কনফিউশন হয়েছিল, ডাউট হয়েছে বলো।
Yes, sir. I have a doubt. In the figure, you have given that y upwards is positive, but you were stating that y downwards is positive. So which one
No.
is?
But in this expression, when we derive this m is equal to ei d2y
Hmm.
dx2, what is the what is the positive x-axis?
Right.
No. Positive x-axis. When we derive, যখন আমরা derive করেছিলাম m is equal to ei d2y dx2, derive করেছিলাম, তুমি খেয়াল করে দেখো আমরা কি কনসিডার করেছিলাম, আসছি। এই দেখো, আমার x অ্যাক্সিস ছিল এটা পজিটিভ, এটা ছিল y অ্যাক্সিস পজিটিভ, ঠিক আছে? হ্যাঁ,
Understood.
এইবার আমি যখন ডিরাইভ করছি, দেখো যখন আমি এখানে আসছি, আমি এটা লিখেছি কি, আসছি, আমি যখন এটা লিখেছি, আমি এই যে এক্সপ্রেশন m is equal to ei d2y dx2 আর ইকুয়েশন a, এখানের অ্যাক্সিস সিস্টেম কি, পজিটিভ এক্স অ্যাক্সিস, x is positive, left to right positive, it is okay. Y positive, vertically upward is positive, that's why we put the vertically upward sign here. Again, this sign convention is for m is equal to ei d2y dx2. Now we
Yes.
try to write down this this moment curvature relationship in this axis system, where x remains as it is, but y is vertically downward, it's positive. When we write m is equal to minus ei d2y dx2, this expression is for the axis system where x is left to right positive, y is vertically downward positive, and slope is clockwise. Slope will be considered as positive when it is clockwise in direction. But in this expression m is equal to ei d2y dx2, এখানে x পজিটিভ হচ্ছে আমাদের লেফট টু রাইট x টা পজিটিভ, y হচ্ছে ভার্টিক্যালি আপওয়ার্ড পজিটিভ, স্লোপ হচ্ছে আমার ক্লকওয়াইজ হচ্ছে অ্যান্টি ক্লকওয়াইজ হচ্ছে পজিটিভ, এই ইকুয়েশন a. বাট ইফ উই রাইট, যদি আমি রাইট m is equal to minus ei d2y dx2 লিখি, সেখানে x পজিটিভ হচ্ছে আমার লেফট টু রাইট পজিটিভ, y পজিটিভ হচ্ছে ভার্টিক্যালি ডাউনওয়ার্ড পজিটিভ, আর অ্যান্টি ক্লকওয়াইজ স্লোপ ক্লকওয়াইজ স্লোপ ইজ পজিটিভ, শুড বি কনসিডার অ্যাজ পজিটিভ স্লোপ। ক্লিয়ার?
Yes, sir. Clear. Understood. Thank you.
Okay, next, this is the case for sagging moment. Now if the bending moment is hogging in nature, then the elastic curve will be like this. This is the elastic curve. From this elastic curve, at the left hand side point, the slope is anti-clockwise in nature. Slope is anti-clockwise in nature. That means it is negative. And slope again, it is at right hand side point, the slope is clockwise in nature. That means this is not negative, this should be positive. It is at this point, the slope is clockwise in nature. That means it is positive, because it is axis system. The slope is, if the slope is clockwise in nature, that should be considered as positive. That means it should be at this point, the slope is positive, left hand side slope is negative, right hand side slope is positive. That means the change of the slope along positive x-axis positive x-axis, it is positive. That is change of slope is nothing but d2y dx2. It is the change of slope. It is positive, but the moment is hogging in nature. That's why it is moment should be in negative. To balance this equation, we have to introduce again just like to previous case. We have to introduce a negative sign. That is m should be equal to minus ei d2y dx2. That means that m is equal to minus ei d2y dx2. This expression is valid for this axis system. That is x is positive left to right positive, y is vertically downward positive, and clockwise rotation or clockwise slope should be considered as positive, for positive both for the sagging moment as well as the hogging moment. Not what we have, just write the summary. That's m is minus eit to y dx2. This is the expression for the moment curvature relationship, and we consider the sagging moment as positive, hogging moment is negative. Deflection, if it is downward direction, that should be considered as positive. Similarly, the slope in clockwise direction considered as positive slope. Now this is all for the theory behind this method of solving the deformation of the beam. Now we'll try to solve a example, that is a simply supported beam subject to the uniformly distributed load. Length is L. We will find the deformation at different location of this beam. Okay, this beam and loading is beam is subject to uniformly distributed load. Now, for what we have this moment curvature relationship, that is d2y dx2 is equal to minus m by ei. That is d2y is related to the bending moment. We need to find out the expression for the bending moment first. For this, at A point or B point, the vertical reaction force, that is WL by 2, and direction is vertically upward from we considered as point at a distance x from support A, and we try to write the expression for the bending moment as mx. That is mx is the bending moment at the point at a distance x from point A. That is support reaction multiplied by distance WL by 2 into x minus bending moment, and the moment due to the support reaction this will generate a sagging moment. That's why it is positive. Similarly, the bending moment due to the external load will be hogging in nature. That's why it is negative. W x square divided by 2. Now we just replace the m in the moment curvature relationship by this expression. That is d2y dx2 becomes minus 1 by ei WLX divided by 2 minus WX square by 2. Now, if we integrate this, we get the expression for the slope or expression for the dy dx. This is dy dx is nothing but the slope of the elastic curve. It becomes 1 by ei minus WLX square divided by 4 plus WXS cube divided by 6 plus C1. C1 is the integration constant. Similarly, the deflection, again, if we integrate this equation for the slope, that gives the equation for the deflection, that is y is equal to minus 1 by ei minus WLXS cube divided by 12 plus WX to the power 4 divided by 24 C1x plus C2. Again, the C2 is the constant for integration. We mark this equation for the slope as equation A, and equation for the deflection as equation number B. Now, what we have to do next? We have to find out the value of C1 and C2 from the boundary condition. What are the boundary condition here? At support A, we have a hinge point. That's why the deflection at point A or deflection at hinge point is equal to 0. or at a or at x is equal to 0, the deflection should be equal to 0. Now from the equation number b, just put the replace the value x by 0, what we get ultimately, we get the value of c2 should be equal to 0. Similarly, at point b we have another hinge there, and then at this point the deflection should be equal to 0, or at point b or at x is equal to l, deflection is equal to should be equal to 0. Similarly, from equation b, just put the value of x is equal to l, and deflection and y should be equal to 0. That's why 0 is equal to 1 by ei minus wl into lq divided by 12 plus wl to the power 4 divided by 24 plus c1 into l. Or if we simplify this, what we get ultimately, we get the value of c1 is equal to wlq by 24. If we write if we put the value of c1 and c2 in the equation b and equation a, we get the equation for the deflection as well as equation for slope. That what we get if we put the value of c1 is equal to c2 is equal to 0 and c1 is equal to wlq divided by 24, we get the equation for the deflection from equation b as 1 by ei minus wlx3 divided by 12 plus wx to the power 4 divided by 24 plus wlq divided by 24x. And similarly, from equation number a, we put the value of c1, we get the expression for the slope, that is 1 by ei minus wlx square divided by 4 plus wx cube divided by 6 plus wlq divided by 24. This is the expression for the slope as expression for the deflection as well as expression for the slope. Now, suppose we try to find out the deflection at the midpoint of the beam. What will be the deflection at the midpoint? Just put at the midpoint the value of x is equal to l by 2. Just put x is equal to l by 2 in the expression for the deflection. We get the deflection at this point, that is y is equal to 1 by ei minus wl divided by 12, x is l by 2 cube plus w to the divided by 24, l by 4 to the power 4 plus wlq divided by 24 multiplied by l by 2. Or if we simplify this, ultimately get the value of y is 5 wl to the power 4 divided by 384 384 ei. As it is positive, the direction of the deflection will be vertically downward. Similarly, at this point, at the midpoint, the value of slope can be obtained if we replace the x by l by 2 in the equation for the slope, that is dy dx is equal to 1 by ei minus wl divided by 4 l by 2 square plus w divided by 6 l by 2 whole cube plus wlq by 24. And if we simplify this is equal to 0. That means in this case, at the midpoint of the beam, the slope should be equal to 0. That means the tangent on the elastic curve at the midpoint is parallel to initial longitudinal axis. Okay, that's why it is the slope at midpoint is equal to 0. Similarly, at slope at point A can be obtained if we put the value of x is equal to slope is at point A is equal to 0. Deflection at point A is equal to 0, but slope at point A can be obtained if we put x is equal to 0 in the expression for the slope. That is dy dx is equal to 1 by ei minus 0 plus wlq by 24. That is dy dx is equal to wlq by 24. As it is positive, the direction will be clockwise. The direction is clockwise. As it is, we have the value of dy dx at point A is positive. That's why the direction is clockwise. Similarly, at slope at point B can be obtained put x is equal to l in the expression for the slope, that is dy dx is equal to 1 by ei minus wl by 4 l square plus wlq by 6 plus wlq by 24. If we simplify this, we get the minus wlq by হ্যালো, এই ক্লাসে আছি রে, বলবি? হুম, 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 হুম। As what we get dy dx or slope at point B is negative and magnitude is WLQ by 24 EI. As it is negative, the direction of the slope will be anti-clockwise in nature. Now we consider second problem. We consider a simplest cantilever beam subject to the point load at the tip. Length is L, and again we have to find out the expression for the moment first. For at a consider a point at a distance x from A, and the expression for the bending moment is P minus P into L minus x. We consider this is L, this is x, and this length AB length is L. That's why distance between the point and the applied load is L minus x. That is L minus x. We consider that is negative because this force gives the hugging moment at this point. That's why it is negative. Now we write the moment curvature relationship again. That is d2y dx2 is equal to minus m by ei. That's minus 1 by ei minus p into L minus x, or PL divided by EI minus PX divided by EI. Again, for expression for slope, we have to integrate the equation. That is theta is dy dx is equal to PL divided by EI into x minus PX square divided by 2 EI plus C1. Again, C1 is the integration constant. At y is equal to PL divided by 2 EI x square minus px cube divided by 6 EI plus C1x plus C2. We have to find out the value of C1 and C2. This integration constant from the boundary condition. The first boundary condition at x is equal to 0. The y is equal to 0 because we have a fixed support here. At x is equal to 0, we have a fixed support. That's why the slope and deformation and displacement is equal to 0. Now from this expressed equation number B, we can easily find out the value of C2 should be equal to 0. Next, at x next boundary condition, because we need the two boundary condition. We need two boundary condition because we have to find out the two integration constants C1 and C2. Now the second boundary condition at x is equal to 0, slope is equal to 0. Slope is equal to 0. At point A, the slope is equal to 0. Then the expression for the slope, that is equation from equation A, if we put x is equal to slope is equal to 0 at x is equal to 0, the C1 will be equal to 0. Now here we can write the slope at point at the fixed support. What we have, that is in the fixed support, just remember the fixed support. If we remove the fixed support, what we have, that is there should be a horizontal force as well. There should be a horizontal force, vertical force, as well as the moment. There should be a support moment. That means if we release the support moment, release the fixed support, there should be a support moment. Due to the support moment, the slope should be equal to 0. As the fixed support has a support moment, that's why the slope at fixed support should be equal to 0. Okay, now from the expression for the deflection, just put C1 and C2 should be equal to 0 in the equation number B. We'll get a expression for the deflection. Y is equal to PL x square divided by 2 EI minus PX cube divided by 6 EI. Similarly, just put the value of C1 is equal to 0 in the equation number A. We get the value of slope, expression for the slope, that is PLX divided by EI minus PX square divided by 2 EI. Now at the tip of the cantilever beam, that is at point B or at x is equal to L, deflection will be equal to, just put the value of x is equal to L in this expression. Y is equal to PL divided by 2 EI multiplied by L square minus PLQ divided by 6 EI, or Y is equal to PLQ by 3 EI. As it is positive, the direction will be vertically downward. Similarly, just put x is equal to L in this equation for the slope. Then the slope at point B will be PL multiplied by L divided by EI minus PL square divided by 2 EI, or PL square by PL square by 2EI. As it is positive, the direction will be clockwise. Okay, direction will be the direction is clockwise at the slope clockwise. Okay, now today আজকে এই পর্যন্ত। তোমাদের কোনো কোশ্চেন আছে? হ্যালো, ডু ইউ হ্যাভ এনি কোশ্চেন?
স্যার পি এর বদলে ডাব্লু লেখা যাবে?
হ্যাঁ,
স্যার পি এর বদলে ডাব্লু লেখা যাবে, মানে ডাব্লু এল কিউব বাই 2EI এল স্কোয়ার বাই 2EI বা ডাব্লু এল কিউব বাই 3EI।
হ্যাঁ লেখা যাবে, নিশ্চয়ই যাবে। কেন লেখা যাবে না?
ওকে স্যার।
That's all for today. Just write in your chat box, just write your roll number. Okay, everyone, just write the roll number in the chat box. And if you don't have any question, you may leave. Okay, I will email this document. Okay, আমি ডকুমেন্টটা ইমেল করে দিচ্ছি তোমাদের। তোমরা চ্যাট বক্সে তোমাদের রোল নাম্বারটা লিখে দাও, দিয়ে লিভ করো, আমি তোমাদের এই পুরো জিনিসটাকে ইমেল করে দিচ্ছি।
Thank you, sir.